Welcome to ChemDoctor, and this is the fourth video in the series on mass spectrometry. And what we want to do in this video is look at how to analyze molecules that have more structure in them. And specifically, we're going to look at the mass spectrometry on propane. All right, so let me write the formula down here. So it's going to be CH3, CH2, CH3. Now, remember that this instrument is used to determine the molar mass of things that we already know the molar mass of, and also unknowns, and in addition to looking at isotope mixtures of particular elements. When we're learning how to analyze the data from a mass spec, it's easiest to look at things that we already know the answer to. So we can calculate the molar mass of propane, all right, and the molar mass of propane is 44 grams per mole. So when we look at the scan on this, the largest peak we should find in the scan should have a molar mass of 44. Now, here's the thing about looking at more complex molecules that the student has to realize, and that is when we inject these things into the instrument and the molecule encounters this electronic beam, this beam of electrons, which, remember, you can consider as being, I like to call the electron beam atomic bullets. So as these bullets are streaming across the hallway and our molecule encounters this beam of electrons, we're going to produce positively charged ions. And in the previous videos, I've described how the instrument works. So one of the things that I strongly suggest is that you make sure to watch these videos in sequence. In any case, coming back to the point, when a highly structured molecule enters this beam of electrons, what's going to happen is that we are going to fragment the molecule. So in addition to producing ions that are going to have a positive charge that will be accelerated down this hallway and into the magnetic field, we're now going to have a stream of particles which will represent not only the ion which has the largest molar mass, in other words, the molar mass of the molecule in question. So here's our molecular ion that should be in the region on our scan that's 44, but we're also going to have many fragments. All right, so when we go to the data, I will take you through how to interpret the scan. Before we move to that, remember that the mass spec is going to give us two types of information. It's going to tell us the mass of the particles that have been introduced into the instrument, and it's going to give us the relative proportions of each type of particle, because the instrument's capable of counting the number of particles that are hitting the detector. All right, so let's go ahead and look at the scan for propane. So this is the kind of data that you get from this, and you'll notice that we've got on the vertical axis the percent intensity. So the tallness of the peak represents the proportion of that particular fragment by comparison to the others. So we've got a fragment here that's at molar mass 29, which actually represents the majority of the fragments that were analyzed in the instrument. Notice that, remember that we already know the molar mass of propane is 44, so we come out here and hopefully you find a peak which is at 44, and we indeed do. I took this scan from real data, and then I just rewrote it here on the video. So you can see right here, this peak, that this is molar mass of 44. So this peak right here represents our molecular ion, which is representative of the total mass of the compound, and specifically it will be this molecular ion. So it's the molecule in total is missing one electron. All right. The next peak in we see is at 43. All right, let me just draw an arrow down. So like I said at the beginning of the video, when we inject the propane into the instrument and it encounters that electron beam, that beam of electrons streaming across the hallway, this particle is going to be ionized, but it also is going to be fragmented. So this next histogram peak to the left represents this particular molecular ion here, or it represents a molecular ion that will have this molar mass. The simplest way for me to write it is just this way, showing that we've lost another hydrogen and so on. And you can continue to work along the x-axis here, which remember is our mass to charge ratio. All right, and the next peak in is going to be so this one is 43. The next one in is going to be 42. The next one is going to be 40. You see that, or excuse me, 41, and then the peak at 40 you see here is almost non-existent. And what that means is that this fragment is actually present in very, very small amounts. All right, so you can walk down this, and I'm going to let you figure this out. Now let's get down here and talk about this series of peaks, which actually represents the largest fraction of particles in the mixture. So the electron beam pretty well blows this thing apart. The biggest peak here at 29 is going to be a molecule that has the following atoms in it. Right? It's going to be something like this. We see that there are 2 carbons in it, which is 12 for each. That's a total of 24. And then we're adding a total of 5 hydrogens, which is a grand total of 29. So this is going to be one of the largest fragments in the particle, or in the stream of particles, I should say. And then I want to call your attention to this guy down here, because basically what this thing lost, all right, is equivalent to this guy here. So this particle that's at 15 for molar mass is equivalent to 1 carbon and 3 hydrogens, all right, which is essentially what this thing lost here, right? The molar mass of this is 29. And if we add 15 to that, we get back the molar mass of the entire compound. So when this thing enters the stream of electrons, at least you're going to see one of the major cleavages is here. So that electron stream is actually breaking a bond between this end CH3 and then the rest of the molecule. All right, and similarly we can move down these peaks. So for example, this guy right here, which has a molar mass of 28, is going to represent, let me just extend this a little bit so I have more room. It's going to represent CH3 CH, all right, for total molar mass. And you can do you can do the same analysis as we move down here, and you can figure out each of these peaks, which I'm going to leave to the student to figure out. So here's the deal. When you're asked a question on a test or a quiz or an exam to identify the compound, and a lot of times they'll give you a list like A through D or A through E, and there will be 4 or 5 different compounds there. What you want to do is calculate the total molar mass of each of those compounds that they're offering you as a possibility for this scan. And then look at your scan and find the peak, which is the greatest molar mass. And that's the way that you can line up in terms of the answers they've given you to what the scan represents. And then finally, before I close, the one thing I want to tell you about this is that in real life, what you're doing quite often as a chemist is introducing a mixture of molecules for which you're dealing with an unknown. And so you're going to go to your largest molecular ion peak to gain information about a possible molar mass of the molecule that perhaps you produced in an organic chemical reaction in the laboratory. All right, and with that, I'm going to go ahead and close the video.